This is the beginning of the third Hermann Otto Hirschfeld lecture, and because we're sort of in this interesting inflection point, not necessarily the number of participants, but in terms of your intensity of attention, we'd like to take this opportunity to honor Roger directly, and it's tradition to do this in the form of a document, and the German word is Urkunde. Okay, so I would like to read this. It's sort of it sounds like such a big deal, but actually it is a big deal because we've been doing this for 7 years now. So this is the Center for Applied Statistics and Economics. That's CASE, is, by the way, the father or the mother of this event, and is honored to have invited Roger Kunker to deliver the 2010 Hermann Otto Hirschfeld lectures on quantile regression in recognition of his contributions to development and dissemination of applied statistics in economics. So I'm going to ask Wolfgang Hertler to pass this Urkunde. It's heavy from the gold letters and everything else to Roger. So Roger.
Pictures, one like that where you show the...
Nothing like a photo opportunity.
You got it? Okay, one more. Because I think I showed this to you already. So this is what we have in the dean's office, right? And so all the names of the HOH lecturers are here. In a few days we'll have his name.
Yeah, we didn't want to do it until we were sure he was going to come.
You don't want to take any chances on this kind of stuff.
So, in this third lecture, I'd like to talk a little bit about some work that I've done in finance, but I should say at the beginning of this that I've made quite a conscientious effort to stay away from finance. I spent quite a lot of time at Bell Labs talking to people in finance, but I really hadn't worked in this area except kind of tangentially on some time series things. But at some point I was drawn back into them partly by Gib Bassett, my original collaborator, who at some point made a migration from an economics department at the University of Illinois Chicago to the finance department there. And partly because we had a kind of long-standing question about whether or not quantile regression had any relevance to doing portfolio optimization. And this is something we had talked about as graduate students, in fact, before quantile regression actually existed, but as soon as we knew about median regression, as we call it now, or L1 regression. There are lots of connections that have been kind of elaborated since then. It's obvious that value at risk, which has become a very important financial indicator, is naturally a kind of quantile regression object, because it's an object that is trying to evaluate portfolio performance as estimated by conditional quantiles. But I'm going to talk about something a little bit different, and it really is just an attempt to try at some level to go back to sort of basic questions about how to measure risk and make some connections with quantile regression that I still think have some potential. And it's potential that none of the three of us who actually worked on this originally, Gregory Cordas was a student of mine at Illinois, he's now in Athens, I think have really too much interest in or ability to pursue, but I keep hoping that somebody else will sort of take this up as a possible avenue of future research. So with that kind of obscure introduction, let me begin by talking just briefly about kind of the foundations of some of the questions that we started with. And they really revolved around the whole question of measuring risk in new ways and making portfolios in new ways. And the beginning of economic thought in this area, or at least my kind of notional beginning, is this work by Daniel Bernoulli on how to evaluate the St. Petersburg paradox. And it's clear that once you start thinking about gambles like the one on the second line, you really need some kind of theory other than expected value of the gamble to make sense out of it, since it's pretty clear that one shouldn't be willing, or people aren't willing to pay an infinite amount to take bets of this type. But then the question is, what are they willing to pay, and how should one think about what they should be willing to pay? And Bernoulli had a standard answer, which was quite specific, and therefore, from my perspective, quite attractive. I'm somebody who really likes the idea that there are simple things that are easily computable, and logarithmic utility in this context is very tractable. And in a certain sense, it had some really attractive properties. Obviously, initial wealth had some very substantial impact on what people were willing to pay for gambles of this sort. And it seems in this context that the kind of curvature of the utility function was enough to explain quite a lot about people's underlying attitudes towards risk of this sort. And so now you can sort of imagine extending these ideas in various directions, and so I've tried to sort of illustrate the what I take to be the major figures in development of expected utility over the 20th century. We've got Frank Ramsey, John von Neumann, Oscar Morgenstern, Jimmy Savage, and Bernardino Finetti. And there isn't really anything much simpler than this idea that we need to just take expected value of utility in order to make sense out of people's aversion to risk. But I'm going to argue that we need something more than that, or something in addition to that. The underlying theory in the expected utility literature is based on a kind of underlying convexity in the action space. I'm going to say just a little bit about axioms and this sort of thing. This is a big topic within decision theory, and I don't really want to get bogged down in too many of the details, but it's certainly true that one needs a little bit of convex structure in these kinds of problems in order to get started with any kind of axiomatic representation of things. But once you have this convex structure, then there's this nice result from von Neumann Morgenstern that with these three relatively innocuous seeming axioms, then you get this result, that there's a linear function, which we're going to call U for utility, on the space script P, such that for all P, Q, and P, we get preferences that are described by just this utility function. And the tradition in the literature has been that the independence axiom is the thing that people like to beat up on. And I'm going to follow that tradition, and I'm not going to beat up on it directly. I'm going to use more illustrious figures in the field to, as by proof by authority or something, that it's worthwhile to think about generalizations. So this Schmeidler 1989 paper is something that is kind of a monument in the history of the development of ideas in terms of weakening independence in these kinds of settings. And I think it was actually a paper written, if I understand it correctly, in the early 80s and eventually appeared in Econometrica in 89. So I, that there are many examples of this sort of thing. But the idea is to, or part of the idea, I should say, was to take the independence axiom and say, instead of thinking about the independence axiom applying to a full set of these alternatives that were earlier specified, that we're going to restrict the class of comparisons in some quite dramatic way to these to this class of pairwise comonotonic alternatives. And so if we restrict the class of the applicability of independence, then as a result we get this bigger class of possible decision rules. And the idea is, in this bigger class of decision rules, maybe there are interesting examples of things that might be able to have some kind of more broad applicability. So, first thing to say something about is what comonotonicity is. I thought that actually this term originated in Schmeidler, but I think that this may not be correct. I would be happy to hear from somebody who knows something more about the origins of this term. But the idea is that if you look at alternatives within this space script P, that those alternatives should order the alternatives in the same way. So if we have actions S and T in this action space S, then in order to be comonotonic, this P and Q have to order those actions in the same way. So P is better in state T than S. That means that Q should also be better in T than in S. But this is not a definition that, at least for me, was terribly intuitive. So I'm going to try to elaborate the definition slightly in order to make it a little bit more digestible for at least people who are coming maybe from a statistical perspective. So one way to think about this is to think about random variables, in a slightly different way to think about it. And so in that context, you can just think about random variables on the same probability space, X and Y, and they're comonotonic if there's a third random variable, Z, and two monotone increasing functions, F and G, such that you can represent X as F of Z and Y as G of Z. And so, in a certain sense, you see that both X and Y have to be basically driven by the same underlying random variable, and that's why they have to produce results that are similarly ordered. The reason that this is a good thing from my perspective, and the reason that it's a very restrictive thing from maybe your perspective or some more general perspective, is that usually when you think about the quantile function of linear combinations of random variables, or in particular addition of random variables, that quantile function has no simple representation in terms of the quantile functions for the two marginals. That is, you could think about X plus Y, and now we have the convolution in order to get the distribution of the sum, and now we need quantile functions of this convolution, but the relationship of that convolution quantile function to the original marginals is rather obscure. But this monotone equivariance that we've mentioned several times now is enough to get you back to this simple relationship that the quantile function of the sum is equal to the sum of the quantile functions for this very restrictive class of comonotonic random variables. And so this actually provides something that's kind of analogous to independence when you think about variances. I mean, if you have independence, then variances can be represented, I mean, the variance of a sum can be represented as the sum of the variances. We know that's a very special circumstance. And if you think about this in the opposite realm, that is, that's a case where the two random variables are completely disassociated, but here the random variables are completely associated, and now we have this kind of additive result that is quite simple. And we'll see that it's very special, it's very convenient, and in this circumstance, it's not that we're claiming that this is common. I mean, there's this kind of phrase, what is it? Independence is the, what's the right word? It's somehow the great fiction of probability theory or statistics. I mean, we're always assuming independence where we don't necessarily believe it as a kind of convenient fiction. Here, I'm not trying to sell the idea that lots and lots of pairs of random variables are comonotonic. I'm merely saying that if we're going to restrict axioms in some way to use this independence axiom in the traditional von Neumann-Morgenstern theory, maybe it would be interesting to restrict it in such a way that it only applied to these very, very special kinds of very strongly dependent observations. So it's really kind of the other side of independence. It's really as if these two random variables are well, I think in the standard non-parametrics literature, this is sometimes called completely concordant, or some phrase of that sort. Another characterization is this characterization of Frichet in terms of maximally dependent random variables. So these well-known Frichet bounds from work by Chuck-Mansky, for example, are really bringing us back into this. I mean, the upper Frichet bound is really giving us basically this comonoton, one side of this comonotonicity. So now the question is, what does this lead to? And the point of the whole thing wouldn't be very interesting if we couldn't have a simple characterization of what the new set of decision rules were. In the original independence axiom, we could imagine doing what we're doing and getting this little u function out. And once we have the little u function, we can make decisions about what the relative advantages are of various gambles or various random variables. And that's all really quite straightforward. What may not be as usual in terms of the exposition of the whole thing is that you can always write this expectation of little u of a random variable y as integral of little u evaluated at the quantiles integrated over with respect to t. So all I've done is this standard change of variables, but it somehow suggests, I hope, that this quantile transformation is sometimes a useful way to, in some way, simplify the usual integral that you would normally write integral over the, say, real line u y df of y. So now the question is, what's what do we get in addition to this little u when we weaken the independence axiom? And the answer is we get two functions rather than one, okay? And one attitude might be, well, we've had enough trouble trying to compute anything with this little u, and now we have like two unknown functions that we need to characterize preferences. But I'm going to try to argue that in certain kinds of decision problems, it is maybe advantageous or even maybe necessary to think about both little u and what I'm calling nu here. And so, as you can see, what I've done in replacing expected utility is just to integrate, instead of with respect to Lebesgue measure in the first line, with respect to this nu parameter. And so now, or nu measure, I guess I really should call it. Now, the idea of this is that we're in effect distorting probabilities. And I might as well admit that right at the beginning, because there is a certain sense in which people are, I think, going to immediately react with horror at distorting probabilities. And there are some really dumb ways to distort probabilities that have been shown various places in the literature to be really quite silly, lead to intransitivity and all kinds of things. But the weakening that we're doing here is something that is a bit smarter than that, and I think has some resonance with everyday life, or at least for me it does. And I'll try to make that a little bit clearer as we go along. But the simple point is that in the usually expected utility framework, the integration with respect to Lebesgue measure means that each probability is getting its original weight, but in the lower expression, each chunk of probability is possibly reweighted by the decision maker in some way that remains a little bit to be explored. This is sometimes called rank-dependent utility, and there's early work by Quiggin, by Yari, I think around in the same time frame as the original Schmeidler paper. Peter Walker, Dieter Dennenberg have worked on this, and there's quite an extensive literature on these kinds of generalized expected value kinds of representations. And so one way to think about this from more mathematical perspective is in terms of Choquet expectations. And there's a kind of very simple standard example that seems to appear in a lot of the literature as a kind of beginning point for thinking about this, and that's to take this measure nu as indexed by some alpha and as this simple function min t over alpha or 1. And then when you apply that, what you get is expected utility, but expected utility only up to some alpha. So what does that mean? It means that you take all the events that possibly could happen as a result of a particular gamble or random variable, and you order them in terms of their attractiveness to you. And then you say to yourself, only bad things happen to me, and therefore I'm only going to look at the proportion alpha of worst possible outcomes, and I'm going to discount entirely the upper 1 minus alpha proportion of outcomes, and I'm going to calculate my expected utility over this lower tail. And if you do that, you know, this is clearly a kind of drastic form of pessimism. It's saying only the worst things can happen. So this is the slogan. Everybody has a relative that firmly believes this. I usually firmly believe this, although the present circumstances sort of have to contradict this to a certain degree, I guess. But it may be like, as observers and listeners, you may be feeling this right now. But in any case, there is, I like to say this is something that must be quite common across cultures, because I keep asking people in various languages if there's some language that they know that doesn't have a word for pessimism. And my feeling so far is that there is no such thing as a language that doesn't understand some notion of pessimism. But if you ask people whether their language knows something about risk aversion or something like that, I think it's probably safe to say that there are lots of languages that don't know about risk aversion.
Can I still represent, I'm not quite clear how you distinguish from the risk-adjusted probability measure. I mean, how do you, this is a much more general concept. So
Right.
do you make a sharp distinction?
I'm going to make a transition that is really quite drastic, in the sense that I'm going to throw away the utility function part and focus on this new part in an effort to sort of see how far we can get with some simple kind of examples in that setting. And then it's a very, I mean, at least to me, it's a very interesting question how to bring both things back in, and eventually maybe to even make some kind of experimental evaluation of how these things actually both work, or might both work, or whether we can do without one or we can do without the other. Okay, another variant of this that's not quite so simple as the other one, but still quite simple, is a one-parameter variant that is this top equation. So nu now equals 1 minus t to the theta. If we think of theta as an integer for the moment, then we can write the expected, or the Choquet expected utility as this thing at the bottom. And now I've already sort of dispensed with the utility formulation, and I've changed variables from u to t, or from t to u, I guess. And then if you look at this thing and you think about it for a while, it takes a bit of thinking maybe. This integral with respect to 1 minus f of x u to the theta has the following relatively simple interpretation. That you imagine anytime you face some kind of gamble, you, instead of getting a single realization, and then that's just what you're stuck with, you have something even worse. That is, the gamble is repeated theta times, and then you always are assuming that you get the worst of those theta realizations. And so that's another kind of very simple, rough notion of pessimism. And it doesn't rule out the idea that you get something very good, but it definitely downweights it considerably. So now the question is, or another question would be, is this really inconsistent with standard expected utility theory? When I was originally working on this, I had several conversations with Victor Chernozukov about this. And he insisted that, you know, maybe you could rationalize this within the Savage framework. But to me, this quotation from Savage is kind of definitive, although kind of definitive is kind of a stupid phrase. But, you know, look at the thing in red, but I think it is clear from the formal definition of qualitative probability that the particular personalistic view sponsored here, and that's the view in the classic Savage decision theory book, does not leave room for optimism and pessimism, however these traits may be interpreted to play any role in the person's judgment of probabilities. So there is a kind of, you're allowed a subjective set of probabilities, but you're not allowed to have two sets of subjective probabilities. And in effect, what I'm sponsoring here, and what I think is implicit or really explicit in the Schmeidler work, and in Quiggin and various other sources that I've already mentioned, is that you have something like a subjective set of probabilities on outcomes, and then you're consciously doing something to distort those probabilities that's influenced by your pessimism or optimism. And it's this dual notion of probability that I think is really anathema to Savage, but I sort of think that it's quite reasonable. So an example that I like to mention, which is one way to start thinking about this, and in fact there has been a little bit of experimental evidence on these questions from kind of survey information about alternatives like this, is to think about two survival curves following medical treatment. Or if you prefer, one survival curve that corresponds to medical treatment and another survival curve that corresponds to non-treatment. So think about the treatment survival curve as the red dashed line, and it turns out that it has some really significant probability of bad outcomes and imminent non-survival. But if you survive till about year 4, if we're measuring the axis in years, then it actually has much better survival prospects than the blue curve. And in the way that I've drawn it, it actually has much better expected survival prospects. Now you could argue that maybe we need to discount survival years in some way, but you could imagine that we've already done the discounting and that this is in efficiency units of survival years or something like that. And now you sort of want to ask somebody, if you're a physician, which of these things do you prefer? And I think for very optimistic people, they're likely to say, gee, I really would think things are going to turn out well and everything should be fine with the treatment. But for very pessimistic people, they may think, gee, you know, I'm not one of those lucky few who are going to be in this big right tail of the survival distribution for the red line. And for those people, they might prefer to settle on a sure thing for 2-year survival rather than the alternative. And the question is there some way that we can distinguish, say, the discounting effect or this kind of utility contribution that would allow us to say something about, you know, whether it's really pessimism or whether it's really the kind of discounting that is at work here. And the answer is that in the experiments that I've seen, one nearly seems to need both things. So standard expected utility theory is putting, in my view, a huge burden on what the curvature of the underlying utility function looks like. And so we have this kind of standard story that utility functions should be concave, and therefore there should be some degree of risk aversion, which we can measure in various ways. But then there are also these kind of funny things, like people are willing to do gambling, you know, in the evening, but in the morning they're like out there buying insurance. And it's kind of hard to reconcile that. You know, there's a long time debate about this, and there's this famous paper by Friedman and Savage and various other things. But, you really don't want to think about like these wavy kind of utility functions that might be used to justify this. Maybe there's some other way to think about it. There are various ways to measure, just based on the utility function, degrees of risk aversion. There's this kind of standard Arrow-Pratt thing. I've always thought the Arrow-Pratt thing was quite weird because I've always thought that variance as a measure of risk was very weird. I mean, I guess a lot of people don't think that it's very weird, but it seems to me very weird to think that risk somehow is symmetric in the way that it thinks about adding to risk based on the lower tail and the upper tail. I mean, to me, risk is somehow about the lower tail, and it shouldn't increase risk if you sort of stretch out the upper tail of the distribution. That should be something that you would naturally think would be a good thing, not something that's adding to risk. But the utility function representation tends to force you into thinking about this because everything is really driven by the curvature, and the curvature then can be somehow approximated by this kind of representation. So there are kind of standard examples of these things. There's this Matt Ribbon thing in which you sort of ask people whether they would take 50-50 bets on with a small positive expected payoff, and then you ask them whether they would take 50-50 bets on much bigger payoffs. And you have to have pretty strange utility function in order to justify this. But a lot of people, say no to the first thing and yes to the second thing without any, hesitation. So there must be something a little bit odd about the idea that most people can decide these things based entirely on a single utility function representation. This is kind of the first indication, or, I think it was, people are still quite, this is still obviously quite a controversial thing, and depending on who you read, people are very, convinced by this or unconvinced by this, but it's something that one needs to really confront, I think, to some degree before being so sure as Savage that the utility function is able to bear the burden of all of the considerations involved in risk under or evaluation of decisions under uncertainty. The example of this that I like is this example from Zurich in which they ask bicycle messengers whether they would take a gamble like this, and most of them say no, but you kind of don't think of bicycle messengers as necessarily the most risk-averse sort of people that you've ever encountered. So it is kind of indicative, and here the bet is actually quite advantageous. I'll come back to another example of this that's more kind of historical interest in a minute.
Can you go back to the actually had to pay for that, or they just got it for free? They were just given that as a gift?
Yeah, they were just given this as a gift, so they don't have to pay anything, but they're still not willing to lose the 5 Swiss francs. So now the question is, can this really be related back to ideas about risk assessment? And in that respect, I'm going to just draw on quite well-known finance paper by Arsenault, Delbene, Eber, and Heath. So this is, I think, pretty well known to everybody who's looked at the value at risk literature, because it was one of the first big things that was very critical of value at risk as a measure of risk. So again, they have an axiomatization. Here, the crucial thing is this subadditivity, and the other axioms are relatively benign, I would say. But again, rather surprisingly, they develop a quite impressive list of standard risk measures that are ruled out by these fairly innocuous axioms. And those include variance, standard deviation, value at risk, and a variety of other kind of related things. Any moment-based thing is immediately ruled out. Then the question is, so what's left? And what's left is our old friend, the simple Choquet measure of risk, or at least it appears as a slightly modified version in which we no longer have a utility function, but we only have this simple integration of outcomes over the worst alpha proportion of events. And this has been introduced in the literature several times by various people. We're certainly not the first people to look at it. And it goes under a whole variety of names, including conditional value at risk, which I always thought was kind of a strange name because it's neither really a value at risk, which is a quantile, or a conditional quantile. It's really like a conditional tail expectation, so you're really just taking the tail of the distribution and taking an expected value over that tail. So the terminology in Artsner, tail conditional expectation, it seems to be in some ways more natural, but you see more expected shortfall, I guess, in the literature, although I have to say I'm not, I haven't been following or doing like citation counts to various terminologies that might be more common now. And so you can relate this back to what we looked at before in this simple way. And the only difficulty is that we need a minus sign in order to make the transition from what we talked about originally with expectations to this risk measure, because of the way risk or losses are actually used as a primitive here. So now the question is, what could we do with this? And one way to think about extending such risk measures is to think about these kind of linear representations in which for different alphas, so alpha is how far up in the quality distribution we go when we evaluate one of these things. We now have some kind of measure on the alphas, and we look at linear combinations of these things. And depending on how we choose this phi function, the weighting function, we get a whole family of pessimistic risk measures. So we can look at this script rho function and evaluate the probabilities, and then it's as if we're just integrating with respect to this nu, and we can interpret nu in terms of the this integral from t to 1 of alpha inverse d phi. So that gives us a new way to think about more general versions, and it turns out that this is the full class of risk measures that are, quote, coherent, according to the Artsner paper. It's a kind of brilliant ploy. I mean, the Bayesians have been very good about this, over a long period, as saying, well, we have coherent decision rules, and the implication is that everybody else has incoherent decision rules. And similarly, here, the Artsner paper is sort of taking a set of axioms and saying, here are the coherent risk measures, and everything else is incoherent. It's a good rhetorical device. I'm not sure that I really want to endorse it. In fact, I don't want to endorse it. I think it's kind of dangerous, kind of rhetorical device in some ways, but it turns out that at least in their framework, their class of coherent measures can be represented this way, which is relatively simple, and I'll give a little bit more explicit examples in a minute. So then we can think about special cases, and a simple set of special cases is that instead of having this general phi of t, we can just have point mass at a few points, and now I've got phi somewhat changed in terms of representation as just a finite set of weights. And then we have Dirac measure on a few points, tau I, on the unit interval. And so now we can calculate what the risk measure is, and we get something relatively simple at the bottom, but it's really better if we illustrate it in picture. So this d phi function is really the step function that we have in the right-hand side, and phi itself is this concave function. So all of the class of these Artzner coherent risk measures give you some concave function above the 45-degree line like this. And they all have this feature that they're all weighting the probability of these bad events more than they're weighting the probability of the worse events. So you can see in the density function, so to speak, panel, the right-hand side, the smallest the smallest third of the worst possible events are getting weight a little bit more than 2, whereas equal weighting would give them weight 1. And then all the weights above that are getting weight a little bit less than 1 or quite a bit less than 1, depending on how far up in the distribution you are. And again, this is just a natural consequence of the fact that the decision maker is somehow changing the weighting so that less favorable events are more likely, at least from his point of view. And when we first wrote this paper, we had a result that I thought was quite nice and quite general, which said that all of these Artzner things could be characterized in the way that I've just described. Unfortunately, there's a very nice Japanese paper on this same kind of topic, and showed the same theorem a couple years before we managed to see it ourselves. But the point is still, I think, worth making, that these simple risk measures that come out of Artzner are kind of very simply characterized as giving distortion measures that are these concave functions, and therefore having this kind of simple behavior, inducing this simple behavior that the less favorable events are upweighted in terms of probability, and more favorable events are downweighted. There's a lot of additional terminology here, which is probably not necessary to go into. So here's a slightly different take on the example that Matt Rabin introduced. And I knew about this as a graduate student, but had kind of forgotten about it. But there's quite an interesting kind of exchange, I guess in the QJE, but I'm not entirely sure about the reference. You should ask me later, maybe, if you really want the correct reference. But the story is that Samuelson came to lunch and offered his department chair a bet of this sort, 50-50, with a quite considerably positive expected value. And Carrie Brown, who was the department chair, refused this bet. And said, no, but I'd be willing to take 100 of these simultaneously. I think maybe this is sort of obviously a good idea, but to Samuelson, it was obviously a really bad idea. And in fact, you need to really do get out your pencil in order to calculate what kind of utility functions are necessary in order to justify this kind of thinking, if you want to call it thinking. Yeah.
When Fair and Goethe did their thing, did the Swiss bicyclists have the same response?
Well, I think so. Yeah. And we'll see that. I think it's a perfectly reasonable response, but not just Samuelson, but John Pratt and a number of people wrote kind of irate papers about this kind of thing, and Pratt actually has a kind of definition of what a proper utility function is that excludes this kind of behavior. So again, this is kind of proof by rhetoric or something, but it's as I hope you'll agree, it's something that if we're really now not restricted just to have any old utility function, but we're only restricted to have proper utility functions, and who better than people at Harvard and MIT to tell us what's proper, right? Then we really are constraining behavior in some way that is quite strange, because it's pretty clear that Cary Brown was quite within his rights. I'm claiming that this is a fundamental misunderstanding of the law of large numbers. That may be a little bit rhetorically over-indulgent on my part, but here's the density, so to speak, of the payoff of 100 of these bets. So it's got a center at winning $5,000, and it's got a really small probability of losing anything at all. So odds of losing money on the full thing is 1 chance in 2,300. So how could you not take 100 of these bets? So you might say, if you were Samuelson, well, it's not this part of the decision that was wrong. It was just the first part of the decision that you shouldn't have been so stupid as to say no to the first thing. But, if you think about sitting there at lunch and, Michael says, here's a bet like this, and you say to yourself, how am I going to explain to my spouse how that I lost $100 or 100 euros at lunch making some stupid bet? It just doesn't seem that unreasonable to say no to the first thing. But it does seem really kind of silly not to say yes to the second thing. So you can do a little arithmetic. And, I've just sort of arbitrarily said we should do something in which we upweight probability in the first half of the distribution a bit differently than in the second half. So this delta 1, this Dirac 1 is what you would have if you only had the distortion delta 1, then it would be just like expected utility or expected evaluation of the value. But the fact that you have a half, delta a half, means that you're upweighting the first half to be twice the probability as the second half, in effect. So you make the calculation. The single bet is got an evaluation of minus 25, so you don't want to do it. The 100 replications has a expected payoff in these terms of $4,000 or something, so you clearly do want to do it. And there are lots of ways to rationalize this, but I do want to emphasize that it's very difficult to rationalize it with just the pure expected utility calculation. So now we come to how this is connected to quantile regression. So it shouldn't be surprising that somehow there must be some connection here. And the idea is that turns out that this funny row, which in LaTeX is var row, is related to the ordinary row that we've seen again and again already today. And if you think about the expected value of this rho alpha, the quantile regression rho alpha that we know and love, evaluated at x minus some c, and we now minimize over c to find the quantile, then the optimized objective function for that looks like alpha times the mean of the distribution of x plus this measure of risk that we've seen from the simple Choquet Artsner thing. So we can always estimate this var rho hat thing by the argmin of a sample of observations on x and make some adjustment by shifting by the mean. And so that means that we can compute things with this in much the same way as quantile regression, because what this Artsner risk measure is doing is in effect measuring risk by the minimized objective function for the usual quantile optimization problem. I don't know, I can't remember exactly where this cartoon figure came from, but I had the impression when I first saw it that it looked a little bit like Art Goldberger. And Art Goldberger is one of my real heroes of econometrics, and somehow I kind of wanted to stick it in. And in effect, that's really all this is kind of the notion that the simple version of the Artsner risk measure, this tail expectation or whatever you want to call it, is really something that's very, very intimately connected with the usual quantile optimization problem. So now we can think about how to do portfolio selection. And the idea is pretty simple. We just, in the simplest version of the thing, we have a fixed y, random variable, and we don't have any portfolio or anything. We just say, okay, let's try to minimize this row, this risk measure, and then have a constraint on mean return. And then when we generalize this, we need to think about y as being now a linear combination of some underlying set of assets, which I'm calling x here. And we choose the first x to be, so the first asset to be numeraire. And then we have this quantile regression problem in which there are differences in the returns of the jth asset from the first one, and then a bunch of portfolio weights, beta, or almost portfolio weights. And then there's this c, which is the rate of return of the quantile of the portfolio. So we're going to optimize over that too. That's the intercept in the regression. And then there's a constraint that says that when we take the mean asset return and multiply by the portfolio weights, we get some required rate of return for the whole portfolio. And then we have to undo the pi's, I guess, in order to get the betas, but the betas are essentially the portfolio weights. And C is the, it's the quantile that corresponds to the minimization that gives you the risk measure. So the optimized value of the first part of the objective function is the risk measure, and the C is the value at risk for that thing for level alpha. So now we have a really, I mean, you know, people like to talk about toy examples. So this is really the ultimate in toy examples, I would say, in the sense that, you know, like a reasonable person who really was knowledgeable about finance would have, at this point, taken real finance data and constructed portfolios and done something more serious. But I wanted to have a kind of stark example which illustrate it a bit more about how this really works in a very simple, kind of intuitive way. So I'm going to look at kind of very extreme situation where I've drawn two densities here in which they're cooked so that they have the same mean and variance. You may not be able to tell that, but if you look carefully, you kind of could imagine that they have the same mean. And you might think, well, they maybe might have the same variance. But they're clearly quite different. And the blue one is somehow much more advantageous than the red one, or at least that's what I'm going to argue. And the way that you can see that, but maybe you can barely see it, is that it has considerably better lower tail performance, which is really important from the risk standpoint. But it also has actually quite a bit better upper tail performance too. And then we could have a little bit of discussion about what's going on in the middle and how that should be viewed. But if you are really sort of fixated, as maybe the value at risk regulation rules are, on the lower tail, you would definitely have to say that blue is better than red. And yet, when you think about standard portfolio theory in the mean variance world, you can't see the difference between these two distributions. They're completely equivalent because they have the same mean and variance, right? I don't know if you can see the green curve, but this is sort of the other side of this. Now that both densities are sort of spread out a little bit more, but now the red curve is actually better. The asymmetric thing has got skewness to the right, and it's actually got better upper tail performance and quite a bit better lower tail performance. And so again, it seems obvious that red is better than green, but it's not possible to see that with the usual mean variance portfolio characterization. So now we put the four things together and we make portfolios out of these four assets. And so what I mean by that is we have a set of data that's generated from these four distributions, and then we try to use that data to make portfolio weights, and then we try to evaluate the performance of the two portfolios. And so I'm calling this simple exercise with the distortion measure, or the Artzner risk measure, or the Choquet expectation, whatever you want to call it, the Choquet portfolio, and the Markowitz portfolio is just the usual mean variance portfolio. And not surprisingly, the usual mean variance portfolio is putting equal weight on both pairs of these assets because it can't really tell the difference. There's always obviously a diversification advantage in investing something in both rather than in just one, but it can't distinguish which one is better in either of these two cases, so it just gives equal weight to the two things. But the Choquet thing is able to distinguish, and it's able to put more weight on the advantageous one in each pair. And one then sees that both in the lower tail and in the upper tail, the Choquet portfolio is doing better than the Markowitz portfolio, and it's in some way pretty clearly better. And this is mainly because, going back to the variance comment that I made earlier, variance in a certain sense is not a very reasonable notion of risk, and at maybe a more fundamental level, it's possible, I think, to argue that the underlying risk measure that is reweighting the lower tail, even if you don't say, well, this is like individually a rational thing to do, maybe you really want to adhere to the usual savage view of the world, but maybe if I'm backed again into a corner, which I sometimes find myself being in many situations, I could say, well, banks may want to do the Savage thing, but regulators may want to do the Choquet thing. And then we need to sort of work that out as a conceivable situation. This, I guess, is just really saying what I just said. I should have mentioned, though, that I mean, as I guess was clear in the previous formulation, I am constraining, I mean, I'm solving this problem at the bottom, and therefore I'm constraining both portfolios to have the same expected return. So it's really a matter of minimizing this measure of risk versus minimizing the usual variance measure of risk as an alternative when we look at this picture. One can do the same kind of thing, flipping the optimization around and saying, suppose we want to fix the measure of risk in some way. In this case, I'm fixing it to be the same Choquet risk. And then we were trying to maximize return. And again, you get the same kind of comparison in the portfolios. The Choquet portfolio is a bit better designed than the Markowitz one. But as you can see, the example is quite cooked in the sense that, you know, we really need a certain amount of asymmetry in the underlying setup in order to make it obvious that the Choquet thing is doing better. But in fact, inherently, because it's using this asymmetric risk measure, I think it's really focused at least on the right thing in to the first order. Yes, this is the slide that I always look at and think I should have called this a grand unified theory of pessimism. It's not really anything other than what we've already talked about. That is that you can approximate these concave functions by something that's piecewise linear and concave. And when you do that, you get a little bit more complicated quantile regression problem, which involves a weighted set of quantile regression objective functions. So now there's alpha indexed by k, and the portfolio weights beta are independent of k. They have to be the same over all k. But the quantiles, the intercepts associated with these portfolios is the quantiles of the distribution of the return distribution of the portfolio are indexed by k. That's this ck thing. And again, we have the usual constraint that the mean return should be fixed. And so any concave function can be mimicked by these piecewise linear representations, and it's easy to solve these problems. In fact, the longitudinal data kinds of things that have been doing that I've worked on a little bit and other people have been working on involve rather similar kinds of optimization problems in which we're stringing together several quantile regression problems and constraining certain parameters to be equal across the set of possible objective functions. It's a little, I mean, it's kind of the other way around in the longitudinal data. In the longitudinal data, we're allowing the betas to vary with quantile, and the intercept is being fixed, intercept representing fixed effects across the longitudinal data are required to be the same for various quantiles. But the optimization is really the same kind of problem exactly. So this original Choquet thing in which you're completely discounting all the good events and focused entirely on all the bad things, which is a kind of extreme version of my grandmother, is maybe too extreme, but any of these kind of concave things can be represented this way, and so there's quite a lot of flexibility. But within that flexibility, everything is completely straightforward in terms of computation. The downside, of course, I guess, is that in the process of looking into this, I've gotten rid of the utility function. So But if you look at the mean variance world, they've gotten rid of the utility function too, for more or less the same reason, that the computation becomes rather difficult. So if you're really going to use only one and you really want to focus on a kind of simple risk measure, this is one way that might be useful. Yes, I think this is still a correct statement, but if it isn't, you can write me and see whether I can send you the code for doing this sort of thing. So that gets us to conclusions. First conclusion may be still controversial, although my impression from talking to people both doing decision theory and economics and people in finance is that everybody seems to have at least one reason to think that expected utility theory is rather unsatisfactory in some respect. You know, I guess the really hardcore Samuelsonians might object, but I think that that's a smaller and smaller minority of the profession. My sense is that these kinds of rank-dependent or Choquet or non-additive or whatever you want to call them, expected utility ideas provide, you know, one source of ideas that may be useful. I like the fact that they're actually easily computable, so that one could actually hope to do something empirical with them. I mean, I'm not ready to go out and start a hedge fund, but I think that it's worth looking at them as an alternative to kind of some standard measures. People have complained for a long time about mean variance portfolio allocation as either relying on multivariate normality of returns or some kind of quadratic utility specification, neither of which seem very reasonable. And in the current environment in which people are talking all the time about tail behavior of asset returns, it's really hard to justify the Gaussianity especially. The last point, I guess, is just the thing that I keep harping on, which is the convenience and the simplicity of the computational strategy. One can do these kinds of frontiers that one sees in the Markowitz theory, and there's lots of opportunity, I think, for additional development of the ideas. And here are a few references, and with that, I will not try your patience any longer.
I have a question about the weighted sums of the quantum regression problem. And the number n, if the number of n towards infinity, the number of parameters assigned, what here is the problem?
Yeah, there's definitely a problem with large M. So large M here means that you put together a very large number of these quantiles. So you're simultaneously estimating, or you're insisting that these portfolio weights hold for a large number of M. Here, in order to get a certain concave function, my sense is that you really don't need more than, you know, a small number, you know, a handful, I would say, of different K. But in the longitudinal data example, definitely there's a temptation to think that it would be nice to use a much larger set of M's. And at that point, unless you have very careful control over the linear algebra of the problem, you may begin to have problems. I don't think that there's really necessarily an identifiability problem. it's when you say you're going to estimate a large number of quantiles. Imagine that you're just doing this over just a single univariate sample. There are certain constraints on the number of quantiles that you would want to do. You don't want to do more than n because there's only n distinct quantiles in the sample of size n. Right? There's only an order statistic, so there's no more information once you've gotten to n. And generally, the Tukey view that 5 quantiles actually summarizes the distribution reasonably well is quite an adequate thing in my view. Although, having spent a lot of time doing, asymptotics for quantile processes and so on, I'm quite happy with the idea that you want to do more than that. But doing more than that usually means something less than square root of n distinct quantiles. Like cube root of n is a typical thing that we sometimes advocate, I guess, around the coffee table in Urbana, but I don't know if we have really any terribly good rationale for that particular rate. And we actually don't agree very well. When I say we, basically I mean Steve Quirkley. He's willing to sort of use fewer, and I'm a little bit more in favor of using more, but there's some thing between 1/3 and 2/3, I would say, as a power of n that I think is reasonable without going too much further than that.
Yeah, I'm wondering if there's any way to reconcile. I understand when you go after mean variance, it's easy to beat up on that straw. But if you think about the work Miles Kimball did on prudence, for example, which is nice because it shows that people can be made with appropriate third derivatives of utility, can be made averse to losses. And then you also even have loss aversion, which is a total dislodging from the base.
Right.
Is there any way to reconcile that work or to link it to this stuff? Or could you think of this as a way of estimating those types of preferences, or is there some sort of link that you've been able to establish between them?
The loss aversion thing is really, I'm certainly not an expert in this, so I may be about to make a big faux pas, but my sense is that one needs a more elaborated theory of how alternatives come to you in order to try to link it directly to this. This is really a kind of one-shot thing, and it would be nice to have some dynamic version of it. Clearly that, as soon as you sort of say, here's how to do portfolio optimization, a natural next question is, how do you do dynamic portfolio optimization? And there really isn't a direct development of that sort at this point. Maybe there could be, but I don't really know what it is. But I should say that, there's a lot of non-expected utility angles to this. There's all the Kahneman-Tversky kind of framing things, and there are some relations to some of that work, but a lot of it actually involves really much different kinds of psychological evaluation criteria. So I think in some way this is really a very narrow outlook that is sort of trying to take a certain very small subset of that kind of psychological motivation and run with it, and factoring more general stuff into it I think is still really very much an open thing. Looks like everybody is as tired as I am.
Local satiation. Okay, so I guess we should close this session and thank Roger with a round of applause. And don't forget there's a reception afterwards. I guess we're all geared up to speed for that, and thanks for coming.